Okay, so we have to now think about what the profile of temperature in the atmosphere will mean for convection, right? We already mentioned that in the water tank experiment, but now we are in the atmosphere with its compressibility effects, right? So pressure change is going to make a big difference. We also need to worry about moisture, right? So this is our familiar hydrostatic equation, which we can write as dP equals minus rho GE G rho E dZ, where rho E is the density of the environment. So this idea of the environment being the large scale atmosphere and the parcel is the small scale motions, you have to constantly carry in your head, where rho is the density of the environment. The gradient of temperature in the atmosphere, remember we already said temperature is not a conservative quantity, because even when we move it adiabatically, temperature changes because of compressibility effects. So dt dz is minus g over Cp, and that is known as dry adiabatic lapse rate. So if you move a dry parcel of air where expansion doesn't lead to condensation heating, and so on, what is the lapse rate? So that is dt dz, just the temperature change with height above the surface if the air is dry. So going back to our favorite figure again, we had rho 1 at Z1, rho 2 at Z2. We were trying to move them around. T2 is using the dt dz relation, assuming now we are in a dry atmosphere, is T1 plus the gradient. So instead of the density gradient, we're just going to use the temperature gradient times delta Z. Very simple equation, kind of the Taylor expansion again. So rho 2 is P2 over RT2, ideal gas law. So Tp of the parcel is T1, we moved it from here to there, minus gamma D, which is this, times delta D, delta Z. Okay, it's just simple equations we're writing again and again. And rho P, the parcel, is P2 divided by RTP. TP is this temperature that the parcel is carrying. Why are we writing it separately? Because it's not it's not a conservative quantity anymore, right? So to simply write this in terms of the dry adiabatic lapse rate, going back to our previous calculations of when this exchange of parcels is stable or unstable, dt dz of the environment is less than the dry adiabatic lapse rate minus gamma d. Remember, gamma is negative, so before we wrote it in terms of just dt dz and said less than 0, greater than 0, equal to 0. What are we doing here? We are basically saying that we are moving the parcel in a background slope of the environment. Okay? It's a subtle complication, but remember the idea of reduced gravity. There is always an environmental gradient, an environmental buoyancy profile, and you are moving the parcel within that environment, so everything is going to be relative. So dt dz of the parcel movement is going to be stable or unstable based on the adiabatic lapse rate of the environment in which it is moving. So if it is less than minus gamma d, it's unstable. It's equal to minus gamma d, means it's basically moving along the dry adiabatic lapse rate. So instead of dt dz being 0 where it's vertically uniform, now you're moving along the dry adiabat. So it's not uniform, but it's just following the same profile as the atmospheric profile, or it's greater than the dry adiabatic minus dry adiabatic lapse rate, in which case it's stable. we'll see a figure that'll make it very clear. Okay, so let's look at a simple scale calculation, dt dz of the environment. You can take temperatures at 500 millibar, so atmosphere is stratified, and there are then pressure surfaces. Remember, we said pressure and temperature can be exchanged because they are so closely related. So you can split the atmosphere into temperature or pressure, but temperature is not conserved, so we go with pressure, which makes life easier in many ways. We'll see later on. So 500 millibar minus 1000 millibar divided by height of the 500 millibar. What does it mean? That means the height of the 500 millibar pressure surface. So it's not a geometrical coordinate, it's a pressure coordinate. So you have to find the height of the 500 millibar surface minus the 1000 millibar surface, which is near the surface but not exactly the surface because it is not a constant. So 270 minus 295, obviously temperature is lower at the lower pressure than at the higher pressure, divided by 5.546 kilometer is the average height of the 500 millibar, or at the location where this calculation is done. 1000 millibar is very close to the surface, 0.127 kilometers, and you get a lapse rate of minus 4.6 Kelvin per kilometer, minus 4.6 Kelvin per kilometer. So from the surface, as you go up, temperature is cooling by 4.6 Kelvin per kilometer. What is the idea? The idea is to get used to the fact that the atmosphere maintains a background profile that depends on whether we are talking about the dry adiabatic profile or a moist adiabatic profile. We'll see that they are not the same at all. And we have typically been just looking at an average measured temperature, which is when you average over the whole globe, you're going to get an average of the moist and dry adiabats. The lapse rate that we have seen is an average. We're getting into more details here because we want to look at the parcels moving and their relative motion with respect to the environmental dry adiabatic lapse rate and moist adiabatic lapse rate, because convection is happening in an environment that's going to determine everything, including how far it goes, whether it's stable, whether it's neutrally stable, whether it's unstable, and so on. Sounds complicated, but just keep listening to the podcast and it's all fairly straightforward. We're just using a few relations again and again, but we are adding complexities in terms of atmospheric properties of compressibility and moisture. That's all.